All right, welcome back to operating systems. So today we're going to cover some odds and ends and do some more stuff with processes because, that's lots of fun. So odds and ends, I looked at your feedback for Lab 0, and some of you are very ambitious and want to create your own operating system. So that's not where this course is aimed, but if you want, I will guide you to a resource, and we should be able to read it and pretty much understand all of it by the time we get through this course. So there is, from the MIT graduate operating system course, there is this kernel, which also has some user utilities that compromises an entire operating system in not that many lines of code for a RISC-V processor that again, you should be able to read at the end of this course. There's instructions, I put it in there to get this repository and run it. You run it as a virtual machine within your virtual machine, so that's really cool. So there's a bit of inception there. So if you want to play with it, you can go ahead and play with it. We should be able to understand it. It's a re-implementation of a very early version of Unix that had less features. So for example, one thing we can now read that is from that is probably their init program. So we talked about yesterday what init would have to do, we talked about that even in lecture 5, what init was supposed to do. So here's what their init does. It opens a console and checks for errors and everything. So it just opens a console if it's not already open. That would get file descriptor 0, and that represents your terminal. In this case, it's just a serial console that represents it because this is a very simple operating system. You probably dealt with like memory mapped serial devices in computer organization, hopefully. If not, just a simple device where if you write to a specific memory address, send some information there. So then what it does is just copy that device for standard out and standard error. So it just duplicates that file descriptor and gets a new one. So file descriptor 0, 1, and 2 will all refer to the same thing. And then it's just a while true loop. It starts init, it forks, gets the process ID, and then if fork fails, well, something bad has happened because all it's trying to do is launch a shell. So if that fails, init fails, and your operating system just doesn't work. Otherwise, if you get a process ID, if you are the child, it does an exec, which is basically exec VE. That will just start running the shell, which is just a program called sh. And that's all it does. And then if it fails, it just prints off it fails, because otherwise exec should transform this process into another program and start running it. So this should only print if it fails, then we get an exit. And then there's a big loop because remember, init has to spawn all the processes and then it gets to adopt everything and call wait on it. So we saw the spawn part, and this is just a big for loop that just does wait over and over again. And it has a check to see if, well, was the child we just waited on, did it represent the shell we created? So if it represented the shell we created, we just restart it. So it just creates another shell process for you to run, and that's all it does. Otherwise, it is something it's not really responsible for. So it just takes a wait process ID, doesn't do anything with the status or anything like that. It just adopted a process, it doesn't do anything, then it just goes through the loop again to wait again and again. So this thing has 2 jobs: to launch a shell, and if you close it, it relaunches the shell. Otherwise, it just waits for everything, and that's literally all it does. So if you want to experiment with your own operating system, you should be able to read that by the end of this course. But again, that's like an MIT grad course, so they hack on it a bit. So you could hack on it a bit, but unfortunately, we do not have all the time in the world in this course. So a few other things when we talk about process scheduling. We can go into really old historical systems that only had a single CPU. Oh, yep.
Just for the MIT thing.
Yeah.
Why did they put like an infinite for loop?
Yeah, so the question is, why does init have an infinite for loop for wait? Because you don't know how many processes you need to adopt, so it just constantly is an infinite for loop that just waits and waits and waits and waits again. Because you have no idea how many children you have to wait for, right? They just get adopted. Yeah, so to go on the historical thing, so back in the day when you only had a simple CPU and the CPU didn't even have kernel mode and a user mode, well, sometimes your operating system didn't need to be that complicated, so they had uniprogramming operating systems, and they only ran one process at a time. So because of this, they were super simple. Two processes can't run in parallel, they can't run concurrently, no matter what. You just launch them, wait for them to be done, and then you launch another one. And that is like DOS back in the day, if you've ever heard of that term. So everyone here is too young for that. That existed, when I was a kid. So multi-programming is what we have now, where we can allow multiple processes. Two processes can run in parallel or concurrently. Those mean the same thing to you right now, but as we go on through the course, they actually mean slightly different things. Modern operating systems just want to run everything in parallel and concurrently as fast as possible. Use as many cores as you have on your machine as efficiently as possible, and that's the job of the operating system. So the specific part of the operating system, if you have multiple processes, and say even in modern ones you could share a single CPU core, well, what do you have to do with that? Well, we already know that to create a process, operating system has to load it into memory, it has to know when to execute it and set up virtual registers and all that stuff. When it's in that ready state, the scheduler is the thing that decides what to run and when, which we'll see in the next lectures. But first, we can talk about the mechanics of actually switching between processes, which we kind of talked about earlier. So to go back, so the core scheduling loop just changes whatever process is currently running on a specific CPU core. So the steps it has to follow is pause the currently running process, so stop it from executing. Save its state so you can restore it later. So this would be all of its registers, for example. Then it would ask the scheduler, what is the next process I need to run? And then it would load that process's state, load all those registers that were saved, set the current CPU registers to equal to those, and then just tell it to run. So, two ways of doing this. We can let processes schedule themselves and kind of opt in for pausing, or we can have the operating system maintain control. So in something called cooperative multitasking, that means the processes have to use a system call to tell the operating system, hey, it's okay to pause me now. Otherwise, you don't get paused, you just keep on running until you exit or you eventually tell the operating system you're about to pause. In true multitasking, the operating system maintains control and pauses processes, and you have no say about it. So for true multitasking, which is what every modern kernel does, operating system can essentially give a process a set time slice, and just whenever it's done its time slice, you say, okay, you're done now, I'll see if something else needs to run, and that decision's done by the scheduler, which again, we'll see later. The other option, if you don't do that, is you can use interrupts on the system. So your CPUs, you can program in timer interrupts. So you can just, before you start running a program, you can have your operating system tell the CPU to generate a timer interrupt after some given amount of time, and then your kernel would get that interrupt, and then it can go ahead and pause the running process and switch it out and do whatever it needs to do. So the process of swapping processes is something we'll call context switching. And we already said at minimum, we'll have to save all the current registers, save all the values using the same CPU as we're trying to save. As you can imagine, there's no good way to do that other than using memory and using a stack or something like that. Sometimes it gets really tedious, so you could look at the MIT code to see what they do. It's just essentially a push for every single register value, and then for a load, it's a pop for every single register value in the opposite order, and you can imagine there's a lot of registers. So on like x86 machines, there are so many registers it will make your head spin. So instead of that, there's some hardware support for saving state, but you might not want to save everything. So like there's a set of registers for special floating point operations, and so on and so forth, which don't make sense to save if your program doesn't use floats at all, for example. Because this context switching, it just takes time where you're not actually executing anything worthwhile. So it's pure overhead, which overhead just means it is work we're doing that is not part of our goal. So our goal is to just run applications. Anytime I spent saving registers to switch between applications, that's time I'm not actually spent running applications. So usually there's a combination of like hardware instructions to save sets of registers at a time, and then software to save as little as possible. So check if this program has ever used floats or ever used any of the big vector operations or something like that. So that's context switching. So we can go into more IPC, because you will see this in Lab 2, which is now posted. Oh yeah, and Lab 1 grade should be back. Pretty much everyone got 100, which means it was probably too easy. So Lab 2, actually you have 2 weeks for it, and it will be much more difficult than Lab 1. But it will still be completely doable, so don't worry about it. So the new API you might see is something called pipe. We looked at it a bit before when we saw that little line operator between processes. So the pipe system call creates 2 new file descriptors for us. So like all the C wrappers, it will return -1 on failure and set error no. Otherwise, this system call returns returns 0 on success. And it takes as an argument an integer array of 2 ints, and it will set those if it is successful. So pipe forms a one-way communication channel using 2 file descriptors, which it sets from the arguments, and pipe FD, whatever the file descriptor is at index 0 is the read end of the pipe, and whatever is at index 1 is the write end of the pipe. And how that works is whatever data you write to the right end of the pipe, well, if you call read on the read end of the pipe, you'll read that data. So it's basically just writing into a kernel-controlled buffer that you don't get to see, and any data you write into it, you can read out from the other end. So yeah, and just as an aside first, so you might see using an ampersand in your shell. So if you use an ampersand at the end of the command, your shell starts that process and returns immediately, so it just forks and just lets that process run, and it outputs the process ID to let you know when it's finished. Just the line character creates a pipe between 2 processes, and I think I posted this on Discord, but just so you have it, this sneaky bash command is actually a fork bomb. So it defines a function called colon, which takes no arguments, and then creates a call to itself, piped with another call to itself, and this ampersand creates that process in the background, and then there is a semicolon, and then it calls it. So it's basically going to do while true fork. So if you really don't like your friends and they're using Linux, you can tell them to execute that and their computer will die. Yep.
How would we even killed your computer once? How do you fix your computer? Did you shut it down and restart? Would that fix everything?
Yeah, so some of them will know that, hey, there's like a big tree of processes caused by a common ancestor, and you could figure it out and kill them all. You could have even written a processor to kill all descendants of something too. Maybe that's a good thing to write. But yeah, I gave up. I just restarted my computer after you guys broke it. So yeah, warning, do not run this command. On the actual machines, you can probably only launch like 30 processes max or something like that. So It won't damage anything too bad, but it'll be annoying to clean up. All right, so, whoops, where is my? All right, so let's just see an example. Me talking is boring. So here is a pipes example to see how to use a pipe. So I will create an array of 2 ints to represent my file descriptors as I give as an argument to pipe. I will call pipe with the file descriptors, and I have a check wrapper which checks if it returns -1. Otherwise, it does something with error no and prints an error and all that stuff. So I just use this to make my life easier and keep checking for errors. So creates 2 file descriptors. I have a write end and a read end. So what am I going to do? Well, I'm going to fork and then check if fork failed. Otherwise, I will do 2 things. So remember what fork will do. It will copy the complete process, everything, no matter what. That also includes file descriptors. So here, pipe would open 2 new file descriptors. So I'll probably get something like file descriptor 3, which would be equal to fd0, which would be equal to the read end of the pipe. And then for the other one, I would probably get 4 in fd1, which would be the right end of the pipe. So I would have those file descriptors open for my process, and then whenever I fork, my child process also has these file descriptors open. Yep.
Could you repeat what check does?
Oh, so check, here, we can just read it. Check will return, or do the call, and not do the call. Check will check if the return value is -1. If it is, it uses the error no, prints a message, and then exits my process. So it's just my error checking, just so I don't have to write if it equals -1 over and over again. Yeah, I just write check over and over again. Okay, so here we have a fork, and then at the time of the fork, they're both copies. Oh, yep.
Is there any reason why when you do in the error checking, you return you exit with the int error instead of just error no itself?
So yeah, so the question is, why do I exit with error instead of just error no itself? And the answer to that is I want to exit and set my status equal to the error no that caused my issue initially. So p-error, if you read its documentation, can actually set error no as well. So I just save it before I call it and then exit with it, exit with the same value because that's the first one. I don't want to see whatever p-error did. Yep.
So for the pipe function, do you not need to specify which file descriptors? Like exactly which,
No, so pipe just takes a pointer to an array and writes 2 values to it.
Okay, so you don't do anything with, you don't tell it, oh, like 3 and 4.
No, I just know that I'm going to get 3 and 4 because by convention, I've said, yeah, by convention 0, 1, and 2 are open, and it will use the lowest number available. So I know it will, if it's successful, I know I'll get FD3 and FD4, and that's the variable I can refer to them as, and that's what they are. Okay, so in the parent, I will create a C string that just says howdy child, and I will take the length of it, and then I do a write system call. So I do a write system call to the right end of the pipe with however many bytes I want to write and the string, and then I just check the number of bytes written, and then the parent would just close the file, close its file descriptor. So the parent would close 3 and 4, close the other ends of the pipe, whatever you want to say, and then finish. In the child process declares a buffer of that magic size, does a read system call on the read end of the pipe, and then prints off whatever the child just read. So when I execute this, whoops. I see howdy child, yep.
Like you
said that the parent would close it, but since it's like not in the if statement, wouldn't like the child also attempt to close it?
Yeah, so the child would also close it. So the child, after the child prints off child read, it would also close their file descriptors.
Okay, so they open the child also opens file descriptors for the pipe.
So the child didn't open the file descriptors. We opened the file descriptors before the fork.
Yeah. So okay, so if you open like just two, like for the pipe,
Yeah.
the parent closes it, then can the child also close it?
Yeah, so the file descriptors are independent for the process. So if I just immediately closed, I immediately closed FD's 1 here, that doesn't affect the other process. It would just close it there, that's it. Yep.
Wait, so in the original, like line 18 is the one that opens file descriptors, right?
Yep.
So then when the child is created, the parent goes through the process and then writes, and then wouldn't it close it? So then by the time the child gets there, wouldn't it be closed?
No, so the question is, well, what might happen is the parent writes to it, then closes them, then how would the child read from them? So remember that the file descriptors, they're independent for each process. So before we fork, we create it, and then we fork, and then both of those processes have file descriptors 3 and 4 open. And if I close file descriptor 3 in one process, it's still open in the other. They don't affect each other. Yep.
But here, you assume that the child did the read after the parent did the write, right?
So here I don't assume anything. So remember, read will block for data. So if for some reason the child executed first, it would just call read, and there's nothing to read yet. It's still waiting for data, so it would get put to sleep. And then eventually the parent would run and then write to that file descriptor, and then the child would return from read.
Okay.
Here, I'll do this first, yeah.
So if the file descriptors from the parent don't affect the child, how is it that when you write to the parent, you write howdy child to the parent's file descriptor, the child file descriptor can read that?
Yeah, so the file descriptors are independent, but you can think of file descriptors as like pointers. So right before the fork, right, file descriptor 3 points to the read end of the pipe, and file descriptor 4 points to the write end of the pipe. And then when you fork, in both processes, 3 is pointing to the read end of the pipe, and 4 is pointing to the right end of the pipe. So they refer to the same thing. So the parent can write to that right end of the pipe, and then the child can read from it because it refers to the same thing. Yep.
So essentially, the pipe will create the file descriptors?
Yeah, the pipe call creates file descriptors.
Then when you call the fork, then those file descriptors get duplicated, 2 for the child, 2 for the parent.
Yeah, so fork, remember exact copy at the time of the fork. So if you have file descriptors open, your child will have file descriptors. Yep.
Not sure if you already answered this, but what happens if you call read from the wrong file descriptor?
So what happens if you call read on the wrong file descriptor? Like if I call read on FD1?
Or sorry, on FD, yeah.
Yeah, so the way that the pipe's implemented, there's like a read end and a write end. So if you try and read from the right end, it'll just return an error from read. So you'll just get an error. All right, did we have another question somewhere? Yep.
Sorry, I'm still kind of confused about how, because you said you think of it as a pointer. So if they're both child and parent pointing to the same file descriptors,
Yep. So their file descriptors are pointing to the same thing.
yeah, so then if you closed it from the child,
Yeah, so
the parent is not affected by that.
yeah, so say both processes, file descriptor 3 is pointing to the read end of the pipe, right? So if in the parent I close file descriptor 3, then it is now no longer pointing to the read end of the pipe, but it's still, this process is still pointing to the read end of the pipe. Yep.
So like it's a question in the ECE itself.
So these do not represent files. So pipe, essentially you can think of pipe as like a kernel managed buffer where whatever data I write to it, I can read from the other end.
So it's just stored in memory, like RAM.
So it would be stored in memory by the kernel. And the kernel makes sure that, you know, yeah, it would be virtual memory. But the kernel makes sure that, you know, you have to have a file descriptor to access this memory because it's part of the pipe and so on.
We can take like that buffer and then we can write to an actual file from that buffer, right?
So if you want to write to an actual file, you just have to open a different file descriptor, right? That actually represents a file because this uses file descriptors. It's reading and writing. This doesn't go to a file. It goes to some buffer managed by the kernel. If I want it to go to a file, well, my file descriptor needs to represent a file. And then what? Where does the parent write to exactly? Like FT3? Yeah, so they're not saved to files. So remember, the pipe system call just creates a buffer managed by the kernel that you can access through two file descriptors, a read side and a write side. And the way it works, whatever I write, so here in the parent I wrote howdy child, and then in the child I read it. So any information that other process wrote to it, I can read it. And that's it. So they don't represent files or anything, even though they're called file descriptors. File descriptors are just a number that represents some resource that I can read and write bytes to. So, yeah, and then what's the question? So any more questions about that? Oh, right, I have another thing. So let's see how much we do understand it. Whoops. So what happens if I do this? So now the parent child doesn't. Yeah, I'm not writing to the buffer. So yeah, the buffer's empty. So what's going to happen in the parent? So the parent just allocates a string and then closes immediately, right? What's going to happen to the child? Yeah, it would get to the read system call. Is that what you're going to say? Yeah, that's true too. Also an orphan. So let's assume that the child runs first before the parent does anything right after the fork. Then the child is going to reach this read system call, and it's going to be put to sleep waiting on some data, and it just gets put to sleep. And then the parent runs. It doesn't use write, so that read will never return. And then the parent goes ahead, closes the file descriptors, returns. Parent is now dead. Child is still waiting on this read, so it should be an orphan, right? So if it's an orphan, if I do PID of pipes, and I think I screwed it, yeah. So if I do PID of pipes, guess what? It still exists because that is my orphan process that just got reparented to init, and it's still doing that read system call. And I never waited on it, I didn't do anything. I just created a poor little orphan, which is now trying to read from a pipe which nothing will ever write to it ever again. Yep.
Is there a timeout on the read?
Yeah, the question is there a timeout on the read? And the answer to that is by default, no. So the kernel's really smart about pipes. So the kernel will know that if no process on the system has a file descriptor that represents the right end of the pipe, it knows that process can no longer get data from the read end of the pipe. So then whenever you call read and it's not possible to get any more data, read would return 0, which represents you can't get any more data, and then it would close, no problem. The problem is, in this case, the child itself still has a file descriptor open to the right, even though it doesn't use them. But because it's still open, even though it's the only process with it and it's waiting on that pipe, it's still possible that that process could write to its own pipe, and therefore it is possible it might get data and then read will never return. So if I wanted to, okay, first, who remembers, I want to get rid of this stupid process. How do I get rid of it? Yeah.
Kill or kill-9.
Kill. or kill -9. Let's try and be nice first. So the normal way is kill, which sends seg term, which is a nice way of saying it. And then I look at, it's gone. Yay, I cleaned it up. I didn't have to resort to violence. So, although, I mean, I could kill -9 and resort to violence immediately. Yeah, so here, if I wanted not to create an orphan process, well, I could probably do things properly, or let's just move this. So in the parent, I'll close both file descriptors whenever I'm done, and in the child, before I do the read, I will close the right end of the pipe, because this is why it gets in good practice to close file descriptors whenever you're done using them. So the child will not use the right end of the pipe, so you may as well close it immediately. So here it will do a read, and then let's go ahead and clean up FD0. And if I go ahead and run that, yeah, unused. Well, I get child read nothing, and that was the output of my child because read returned 0. And if I check, I didn't create an orphan. Cool. So we fixed it. Yep.
Sorry, could you explain why we get an orphan in your previous implementation?
So yeah, the question is, if I move here, this here, basically, why do I get an orphan? So the kernel is smart. So the only way that you can read data from a pipe is if someone writes data to a pipe, right? So the kernel knows for every process how many of them have a file descriptor that points to the right end of the pipe. And the rule is, as soon as there are no more references to the right end of the pipe, the kernel knows you can't add anything to it, so that would send like an end of file notification to it where read returns 0. So in this case, where I had the orphan and I had the close at the end, well, I did a read and I still had one process with the right end open, and it was me, right? So it's super unlikely, but I could have had a single handler that wrote to that if I wanted to, or something odd like that, right? Even though it only had one core or something like that, it's still possible through signals, so it has to be conservative about it. Yeah.
So in Linux, there's another command called kill all.
Yeah.
What does that do? Does it kill like all of the processes with? Does it kill all like child processes?
Yeah. So there's a question: what does kill all do? So kill process by name. So yeah, it just kill all. I believe will just kill takes a process ID. So kill all will take a process name and then send it to all processes that match that name. So you could write this by now, right? So it just opens proc, looks to see if there's a match, and then it can look up its process ID and actually do the system call that actually does that.
There's also like another command called pkill.
Yeah, so pkill, it lets you use just a process name. So no one really knows process IDs. Yep.
If the write is still there in the parent, can we still close FDS1 in the child, or would it be a problem if the child executes first and then the parent has to read the write?
So the file descriptors are independent in the processes. So even if the parent closed them immediately and executed first, the child would still have file descriptor 3 and 4 open. So they don't affect each other.
So we can also close FDS1 0 in the parent as well?
In the parent, like if I, like,
If write is still there in the original FDS0, yeah.
yeah, I close both of them in the parent because it doesn't really matter. In fact, I could just not close anything in the parent because the parent's going to exit anyways and they'll get cleaned up by then. Yep.
Just to clarify, the file descriptors are copied when you fork.
Yep.
Okay.
Yeah, file descriptors, literally, the processes are exact clones of each other at the time of the fork. So all the file descriptor numbers are the same for both of them, and what they point to and what they represent are also the same. Yep.
Can you write to those file descriptors from outside of this process, like using the terminal?
So the question is, can I write to those file descriptors from outside of the terminal? So for this, there's no way to actually, aside from that system call that returned these file descriptors, like we said, this doesn't actually represent a file or anything like that. There is something called a name pipe that will like add a path that you can access it to, and then other processes could use that name to open these file descriptors. But for this, the only way to share these file descriptors is through just getting inherited by fork. Yep.
Is there a way that instead of making the file descriptors pointers, could you make them local variables or variables instead of pointers?
So the file descriptors are all managed by the kernel, so you don't get to pick. Yeah, and then what the file descriptors? Yeah, so ideally, you would have to close them in both processes if you're being nice and closing them as soon as possible. So in this case, whenever I did the correct thing, well, at the time of the fork, file descriptor 3 and 4 are open, but if I go back here and look at my code as it was before, well, at no point in the parent do I ever use FD's 0. So what I should do is close it immediately in the parent because I don't use it. And then I'll write to FD's 1 and then close it when I'm done with it. And then in the child, it should be the other way around, right? It never uses FD's 1, so I should close it immediately in it and then do the read and then close it whenever the child's done with the read, right? So I should close my file descriptors immediately. Yep.
If you were to reassign your file descriptors before you close them, would they still be open?
Like the variables?
Yeah, like if you were to say like, I don't know, assign the file descriptor to something else right after pipe, would it like leave the file descriptors open?
Yeah, so there's a question if I like assigned it to something else or?
No, I mean like if you did FD1 equals something else, equals, I don't know, whatever, yeah, like yeah.
So if I did something like that, remember the kernel is just taking the file descriptor number and it represents something to the kernel. So right now I have file descriptor 0 to 4 open. If I just make up 5 and try and read the 5, what does 5 represent? Nothing. What would you expect to get? An error, right? It'd be like file descriptor 5 isn't open, doesn't represent anything. I don't know what the hell that means. Okay, so cool. So let us get into what you can expect to see on some exams and like problems they like to ask you. So fork gets really confusing real quick. So here's from this. So for each, so this was one of the questions for each program shown below. State whether it will produce the same output each time it is run, or whether it may produce different outputs when run multiple times. Explain why it behaves like this. And it does a bunch of forks, which is of course fun. Oops, iPad. So, oops, ow. Okay, so in this case, anyone want to tell me what this does immediately? Yep.
It just runs a while loop and then like it just keeps forking and forking until the iterator becomes 0.
So how many times will I see, how many processes will I get and what output will I see?
You'll see like 16 processes. 16, I think.
Okay, so you got 16?
4 squared, 64.
64, wow. So remember this is an exam question, you have to,
4 squared is 16, my bad, it's 16.
16? So this is an exam question, so student reasoning, do I want you to print out 16 things? Actually, 16 is not too bad, 64 is bad. 16 might not be too bad. Okay, if there's 16, what would each of the 16 processes print? Yep.
The I value of the iterator.
The I value, so what? But it starts at 4 and goes down to 0, so what am I going to see, like 4?
Yeah, 4, 3, 2, 1, 0. No, you won't see 0.
4, 3, 2, 1 for 16 processes?
No, you'll see 4 for like
Oh.
one process, and you'll see like 3 for like 2 processes.
Times 16?
No,
Times 4.
Each process will print I.
So see 4 4s, 4 3s, 4 2s. Yeah.
I think you only see 4, 3, 2, 1, right? Because there's an exit 0
Yeah, and the else
on the parent.
so the parent would exit.
So the parent won't fork afterwards.
The child's become, okay. Let's just go, let's start at main. So if we start at main, let's say we have process ID 100 that starts executing main, just because I like the number 100. So this process starts executing main. What's it do first? Declares a variable called I and sets it equal to 1. So I'll just set what it has I equal to here. So I equals 4. Okay. It will check this condition. Does I equal -1 or does I equal 0? No, so we'll go into this loop. So this process will go into the loop and then call fork. What happens when I fork? When I create a child, process ID 101 probably. Is it going to have an I? What's the value of I? And here, I'll write in the corner here the parent-child relationship. So process 100 had a child called process 101. So we created 2 processes. Which one's going to run first? Don't know. Let's, for the sake of argument, let's say the parent runs first. So the original one runs first. What would fork return for it? 100? 101. Whoops, that was a giant eraser. So its fork would return 101, and then it assigns it to a new variable called PID. Okay, just so we're here, the child, what would it return from fork? 0, and it also assigns that to its variable PID. Yep.
So this might be a random guess, but is it going to be 4 factorial times 3 factorial times 2 factorial times 1 factorial?
Let's get through it. Yes, we got a factorial response. Let's see what happens. So we can argue about, let's say the parent starts executing next. So the parent starts executing. Is PID equal to 0? No. So it would hopefully fall in this else branch, and then it would, what would it do? Print 4, and then exit. So it would be donezo, right? It doesn't exist anymore. Okay, so we don't have to argue about it anymore. Great. So what would process 101 do? So 101 was at the fork. So it would check this if statement, is PID equal to 0? So it would take update its I from 4 to 3, and then it would fall out of this loop. So it would go from here and then go all the way back up to check the condition. So is I equal to 0? No, so we have to go into the loop. Now it forks. So process 101 is forking. So what process would it create? 102. This is where we're glad we're engineers. We don't have to like name children all the time, because I'd run out of names by now. What's its value of I? And PID is a local variable that doesn't exist yet in either of them, so it would have been refreshed for both of them as soon as it exited the loop. So now, in process 101, what does fork return? 102. So PID equals 102 for this process. What does fork return for process 102? 0. You can see this kind of gets, well, not tedious, but it's not terribly fun. All right, so at this point, which one runs first? No idea. Let's say 102 runs first for argument's sake. So it would go, it would check right here, this if condition. Is PID equal to 0? Yes, indeed. So it would decrement I. So it would decrement I from 3 to 2. Would it also do this? No, why would it not do that? It's I. Yeah, they're separate processes now. They're independent of each other. So one updating its I doesn't update the other's I. So this is now 2. So imagine telling yourself that in 105, that updating I doesn't update I. Yeah. So how much we've grown. So in here, yeah, we just decremented I, and then it would go back up to this line. Is I equal to 0? Or,
Okay, I have a question.
Yep.
So when we used pipe before and we put it before the fork, both the parent and the child could reference it and like kind of like modify it.
Yeah.
So if you have a pointer instead of like an integer, would the parent and child be able to like communicate with each other through that pointer?
No,
No?
because they're independent, right?
It does that.
So the reason they can share file descriptors is the kernel is managing that, right? It's not represented by memory or anything. It's a thing represented by the kernel. So that's why it can do it. Yeah. All right, so where were we? Yeah, so we're at the loop. Does I equal 0? Okay, so what does process 102 do then? It would call fork. What would we create? Yep.
You create another child, but why isn't P101 dead yet?
101's not dead yet because we said it didn't execute first. We said 102 did this time. Because we didn't know which one was going first, so I just said, let's just say 102 goes.
Okay, but 101 is not gonna, it should just print 3 and then die.
Yeah, 101, whenever it starts running, will just print 3 and die. But we haven't said it's running yet. So, okay, so 102 just called fork. It created 103. So PID got reinitialized. So what does fork return for 102? 103. What's the value of I in 103? 2. What did fork return for that process? And here is our parent-child relationship. So 102 was a parent of 103. So we just have a big linear line of processes. So now what's going to happen? Well, we can see that if 102 executes, well, it would check this statement. Is PID equal to 0? Nope. So it would hit else and then print off its I. So this would print 2 and then exit and it's dead. All right, well, let's say 103 goes first. Let's say we get the fun order. So 103 goes. Is PID equal to 0? Yes, it is. So we would update I to be 1. Whoops. 2 to 1. And then it would go for the loop, and eventually it would create, so I'll do this fast mode. So it would eventually create a new process that gets ID equals to 1. This would get process 104. this would get process ID 0. In this case, this process, it would check it. I goes from 1 to 0, then it would go to the back of the while loop, and then it would check if I is not equal to 0. Now it is equal to 0, so this process would just quit immediately. And the other processes we kind of know this would print 3, and this would print 1. So we would get 4, 3, 2, 1 in any order. We don't know what order they would be in. So yeah, so the one you should do that is actually easier is it just puts a wait PID in the else statement. So then you should be able to answer, well, what happens now? Is there a specified order, or is it still the same thing? So that's it. Just remember, bone for you. We're all in this together.